Yeah, CRM, I think I have made you a presentation.
Yeah, good morning, everyone. So, uh, we will continue with the study of hazards. So, what happened? Oh, one second. Yeah, so we'll continue with the study of hazards. So, the aim is to, so you have studied this Queen McCloskey's technique for logic minimization. So the aim will be to understand how we can perform logic minimization in the presence of hazards, or you can say to avoid hazards. So let us look at a few definitions. So, so first, how do you study hazards? So we consider monotonic transitions. Okay, monotonic transitions. So let me also. We consider monotonic transitions. See, that means, see, if your input change is non-monotonic, then you could expect, so non-monotonic, it's only expected that you will have some non-monotonic transitions in the output. Okay. So if you have non-monotonic transitions in the input, you can very well expect non-monotonic transitions in the output. Okay. So to study hazards, what we consider is we consider monotonic transitions in the input. Monotonic transitions means 0 to 1 or 1 to 0. These are, monotonic transitions. So suppose you have, say, monotonic transitions. If you have monotonic transitions, then you would expect monotonic transitions in the output. All right, so you would expect monotonic transitions in the output. So, I mean, either way, either this way or this way. So if not, then see, so what are hazards then? So hazards are basically undesirable. You can say undesirable changes in undesirable, you can say transient. Undesirable transient changes. So you have already seen, I mean, it is already explained to you. We have also, I mean, both of us have explained to you. So when you say undesirable, I mean, so suppose, you know, you can have two situations. You expect your waveform to be, say, you expect your waveform to be, say, you know, like this, or you might expect your waveform to be like this, but you have some, you know, this is your undesirable spike. These are your undesirable transient changes. These are also called spikes or glitches. All right. So these are things that you don't want. So this, you know, this level is 0 and this level is 1. So this is called a static zero hazard. And this is called a static 1 hazard. This is called a static 1 hazard. Why? Because positive spike when output should be low, and similarly in the other case you have a negative spike and the output should be high. So this is a static one hazard. All right, and what we have already shown over here, there is a fundamental mode of operation. This you have already studied, but just repeat it again. That is input transitions happen only when circuit is stable. So this is your, this is your fundamental mode of operation, and there again you have this thing, you have this single input change, or you can have multiple. So this is of course the single input change. And then you also have all right. So so this is the one. I mean both can be studied. So single input change is easier to handle. All right. So we have this, these definitions. These are written here. Now you can also have dynamic hazards. So dynamic hazards are situations where you can have multiple changes. So you can have dynamic hazards. Means multiple changes may happen. All right. So let us see some examples. So first of all, let us understand the concept of function hazards. Okay. So now what you're saying is that your input, so input is, how do you represent your input? Input is represented by a mean term. All right. So if you look at this diagram, this function which is shown there, so there the function is changing from, say, mean term 1 corresponding to mean term, I can say mean term, if you say A bar, B bar, C bar, D bar, this corresponds to the input, and you're having change from 0, 0, so A bar, B bar, C bar, D. So this corresponds to. All right. So this is your initial input. This is your initial input, and this is your final input. All right. Now, so here, of course, these two cubes are adjacent to each other, and you can expect monotonic input changes, right? So here the input change is monotonic, only, basically only this part is changing. This part is changing, okay? So it's a monotonic change of, you can say, monotonic change. Having a transition from 0 to 1. All right. So that is a change which is happening. All other inputs are steady. So if you look at this, that is the function which is shown over here, So now here, what do you see? So here, what you see is that you know, if here in this case, call it say f1, I mean, I think, well, these are the same functions. So f0, 0, 0, 0. In this case, all right. So output, output is steady. Okay. So here you have the output steady. Here the output is steady. So what you're seeing is that in this case, the function doesn't change. Now suppose your implementation, I mean, this was actually, I think, covered in the class yesterday. So suppose your implementation was actually this thing, that is, A bar, B bar, C bar, D bar, or I mean, if this is your implementation, then you have a problem, all right? So let me just copy this. So this is, let us say this is, these are all zeros. And this is 0, 0, 0, 0, and this is. So we are, well, maybe I can just keep a copy of this. So here we are we're looking at this. Okay, so here the function. So we were looking at this implementation. This is the implementation that we are looking at. Sorry. I mean, this is obviously a non-optimized implementation, but I'm just explaining the problem. So if you have this implementation, so you basically have, you basically have two mean terms here. You are basically taking this mean term and this mean term. And what will happen is that, oh, okay. Sorry, I've been saying certain things. So this is really not what I want here. This is really not what I want here, because the output of the function is 0. So this is not the implementation. Okay. So this is not what I want right now. I'll just explain it. Well, let me just cut this out. Okay, let me just modify this function just for this discussion. Suppose this was instead of 0, suppose it was 1. Okay. I mean, I'm just taking this function. Suppose instead of 0 it was 1. Then, of course, yeah. Suppose it was 1. Then this is all right. So then we are taking this main term. And in this case, what might happen is that, so you're basically taking, these two cubes. You're basically taking these two cubes, and as you make a transition, you can say, f1 is this function, and f2 is this function, and your I mean, just if we focus on this part, if we just focus on this part, we can say f dash is f1 or f2. Now, what happens is that, f1 is true only for this input, and f2 is true only for this input. So you have, you have this situation. You have this situation. So input is, changing. So at some time t, you have this input, and then you have this input. So your output, let us say, so so your output, this one is say falling, and this is one function, and the other function, say this is the other function that is rising. So in the meantime, what you can have, you can have a glitch. So this is, it is 1, goes down to 0, and then you have. So this is, as you have seen, it's a static 1 hazard. Of course, you have already seen that if you use, if you use, this blue cube, if you use this blue cube, if instead of this, you use this cube, that is A bar, B bar, C bar, then of course you don't have this problem. So if you use that cube, so that is 1 all the time. So, or let me just put it here. So this one is on all the time. So you don't have a problem. You don't have a problem with this. So if you have this kind of a function with this part, so for this input change, yeah, so you have the concept of what we call a transition cube. Transition cube, this is the cube transition cube. So this is your input changing from mean term M1 to M2. So transition cube is the cube containing both M1 and M2. Of course, this is actually the smallest cube containing both M1 and M2. So this transition cube, if M1 is say you have so here say f is a function on say x1, x2, xn, and so M1 is say literal 1, literal 2, literal 2 and literal n. So Li here Li is in xi or xi bar. So it is either xi or xi bar. Okay, so that is what Li is, and M2 is, let us say, L1 bar, L2 bar, Ln bar. So the transition cube of M1 and M2 is L1 or L1 bar, L2 or L2 bar, Ln or. So this is, so basically if you have, so let us see the transition cube. So earlier our cube was, the cube that we are considering is 0, 0. I mean, or rather we can say A bar, B bar, C bar, D bar. And M2 was A bar, B bar, C bar, D. So transition cube of M1 and M2, that is, you have A bar or A bar, B bar or B bar, C bar or C bar, and D bar or D. That is equal to A bar, B bar, C bar. All right, so that is how you get the transition cube. All right, so this is the idea of a transition cube. So now going back to this function, going back to this function. So anyway, I did this on this either way. So if you consider this input transition, so let us say that this is your, let us say this is your, or we can choose some other color, light green. So if you say that this is your, this is your transition cube, all right, this is your transition cube. This is a transition cube. So in this transition cube, the function changes monotonically. All right. So the function changes monotonically. So given function may change monotonically. within a given transition queue. T for the input for the input changing from M1 to M2. All right. Given function, of course. Given function may change monotonically within a given transition queue. So, I mean, that includes no change. All right. So, in that case, you say that the function doesn't have a hazard in T. All right. So the first thing is that your function shouldn't have a hazard, because we'll consider the other situation when the function does have a hazard. So that is over here. We had this other situation. So let us take this, that side. Let us consider another transition queue. So we don't want to consider this queue right now. We don't want to. So we are interested in a different queue. So let us look at a different queue. That is, we are looking at, say, this transition queue. Okay. And so here, what is M1? M1 corresponds to, so here we have, this is AB and this is CD. So M1 corresponds to A bar B, A bar B and C bar D bar, and M2, that is this one, that is AB C bar D, AB C bar D. Okay. So now you see you have two ways of, I mean, if you consider a single input change, so you could either change this way or you could change this way. And let me just put it a little differently. or you could change, it's a little tight. Or you could change this way. Now, when you change this way, that means your input is changing from 0, 1, 0, 1 to no 0, 1, sorry, 0, 1, 0, 0 to 0, 1, 0, 1 to this thing is 1, 1, 0, 1, 0, 1. So this is a monotonic change, right? This is a monotonic transition, monotonic. These are monotonic transitions, but look at the output. So the output is not monotonic. So the output is, this is 0, this is 1, this is 0. So this is not non-monotonic. Okay, this is non-monotonic, and this is, so here you have, you have a function hazard. So here you have for M1 to, okay, so this is a function hazard. So there is nothing that if your function itself has a hazard, then there is nothing you can do about it. All right. There is nothing you can do about it. So when we talk about avoiding hazards, we only consider the cases. So nothing can be done about function hazards through implementation. So only seek to avoid hazards in the absence of function. All right, so this is the first important thing, that we seek to avoid hazards only when you do not have a function hazard. All right. All right, so I think let us stop here today. We'll continue.
So CRM, one discussion the students wanted about the evaluation procedure so that they can decide about the online and offline exams.